The cosmos is an ever-evolving theater of incredible phenomena, and among its most spectacular displays are galactic collisions. These immense events unfold over millions or even billions of years, reshaping the structure of galaxies and fostering the birth of new stars. A galactic collision is not a rare occurrence in the universe but rather an integral part of its evolution. To truly understand the scale and significance of these events, one must first grasp the structure of galaxies and the forces that govern them. Galaxies, vast systems of stars, gas, dust, and dark matter, range in size from dwarf galaxies with just a few billion stars to giants with hundreds of billions of stars. They are not isolated entities, instead, they are gravitationally bound to other galaxies within clusters and superclusters. These structures are in constant motion, influenced by the gravitational pull of their neighbors and the overarching expansion of the universe. While the vast distances between galaxies might suggest isolation, their gravitational interactions often lead to collisions, particularly within dense clusters. Contrary to what one might imagine, galactic collisions are not violent events in the traditional sense. Individual stars within galaxies are so far apart that direct collisions between stars are exceedingly rare. Instead, the interaction primarily involves the gravitational forces of the galaxies, which distort their shapes, redistribute gas and dust, and trigger intense star formation. These interactions can also lead to the merging of the galaxies into a single, larger entity. The process of a galactic collision begins when two galaxies come within each other's gravitational influence. As they draw closer, their mutual gravitational forces distort their structures, stretching them into elongated shapes called tidal tails. These tails are streams of stars and gas that are flung outward, often creating stunning visual patterns. The Milky Way and the Andromeda Galaxy, for instance, are expected to produce such features when they collide in about 4.5 billion years. During the collision, gas clouds within the galaxies compress and collapse, igniting bursts of star formation. This phenomenon, known as a starburst, can lead to the creation of millions of new stars within a relatively short period. Some of these stars are massive and burn brightly, eventually ending their lives as supernovae, enriching the surrounding interstellar medium with heavy elements. The newly formed stars and their remnants contribute to the evolution of the galactic structure, adding complexity to the resulting system. Galactic collisions also play a critical role in the growth of supermassive black holes, which reside at the centers of most galaxies. As galaxies merge, their central black holes are drawn together, eventually forming a single, larger black hole. During this process, the inflow of gas and dust toward the black holes can create active galactic nuclei, among the brightest objects in the universe. These luminous centers emit intense radiation as matter is accreted onto the black hole, providing a unique opportunity for astronomers to study these enigmatic objects. One of the most famous examples of a galactic collision is the Antennae galaxies, located about 45 million light-years away in the constellation Corvus. This system, formed by the collision of two spiral galaxies, showcases dramatic tidal tails and regions of intense star formation. Observing such systems provides valuable insights into the dynamics of galactic interactions and the processes that shape the universe. The outcomes of galactic collisions depend on several factors, including the masses, relative velocities, and angles of approach of the colliding galaxies. In some cases, the galaxies merge to form a single, more massive galaxy, often an elliptical one. In others, the galaxies may pass through each other, separating but leaving behind significant structural changes. In rare instances, the collision can lead to the complete disruption of one or both galaxies, scattering their stars and gas into the surrounding space. As our understanding of the universe has deepened, so too has our ability to simulate galactic collisions. Advances in computational power have enabled astronomers to create detailed models of these events, allowing them to explore scenarios and predict outcomes. These simulations not only reproduce the observed features of galactic collisions but also provide a window into the future of our own galaxy. The impending collision between the Milky Way and the Andromeda Galaxy, known as M31, is a subject of great interest to astronomers and the public alike. Currently separated by about 2.5 million light-years, the two galaxies are on a collision course, moving toward each other at a speed of approximately 110 kilometers per second. Despite the vast timescale of the event, simulations have revealed a detailed picture of what is likely to occur. The collision will begin with the outer halos of the galaxies interacting, followed by the merging of their disks and central regions. Over billions of years, the galaxies will settle into a single elliptical galaxy, likely surrounded by a halo of scattered stars. While the idea of a galactic collision might seem apocalyptic, it is essential to remember that these events are natural processes that have been occurring since the universe's earliest days. They play a fundamental role in shaping galaxies and driving cosmic evolution. The redistribution of gas and dust, the formation of new stars, and the growth of supermassive black holes are all critical processes influenced by these interactions. Galactic collisions are also a testament to the power of gravity as the dominant force shaping large-scale structures in the universe. Despite the immense distances and timescales involved, the outcomes of these collisions are governed by the same physical laws that dictate the motion of objects on Earth. This universality of physical laws underscores the interconnectedness of all phenomena in the cosmos, from the smallest particles to the largest galactic structures. Understanding galactic collisions not only enriches our knowledge of the universe but also provides context for our place within it. The Milky Way's eventual collision with Andromeda is a reminder that even seemingly static structures like galaxies are dynamic and ever-changing. By studying these events, we gain a deeper appreciation for the complexity and beauty of the cosmos. Galactic collisions are not isolated events but part of a broader tapestry of cosmic evolution. The universe, in its infancy, was a hot, dense state dominated by a nearly uniform distribution of matter and energy. Over time, tiny quantum fluctuations in this early state were amplified by gravity, leading to the formation of the first structures. Small proto-galaxies began to form, merging and interacting to create larger and more complex systems. This hierarchical process of galaxy formation and evolution is driven by the interplay of gravity, dark matter, and baryonic matter. Dark matter, an invisible and enigmatic form of matter that makes up about 85% of the total mass in the universe, plays a crucial role in galactic collisions. Galaxies are embedded in massive halos of dark matter, which extend far beyond the visible components of the galaxies. During a collision, these halos interact gravitationally, influencing the dynamics of the event. Dark matter also acts as a scaffolding for the formation and evolution of galaxies, dictating their large-scale distribution and clustering in the universe. One of the most striking aspects of galactic collisions is their role in driving starburst activity. The compression of gas clouds during a collision triggers the formation of massive clusters of stars. These starburst regions are often visible as bright, blue patches in the optical spectrum, signaling the presence of young, hot stars. In addition to optical observations, these regions can be studied in other wavelengths, such as infrared and radio, which reveal the intricate details of the gas and dust dynamics. However, not all gas in colliding galaxies is consumed in star formation. Some of it is expelled into the intergalactic medium through powerful winds driven by supernova explosions and the activity of supermassive black holes. This process, known as feedback, plays a critical role in regulating star formation and enriching the intergalactic medium with heavy elements. These metals, forged in the cores of stars and ejected into space during their deaths, are the building blocks of planets, life, and everything we see around us. Another fascinating outcome of galactic collisions is the formation of peculiar and irregular galaxies. These systems often exhibit unusual shapes, such as rings, bridges, and tails, which are the result of gravitational interactions. For instance, ring galaxies, like the iconic Cartwheel Galaxy, are thought to form when a smaller galaxy passes through the center of a larger one, creating ripples of star formation that propagate outward like waves on a pond. Similarly, tidal bridges and streams are formed as material is pulled from the colliding galaxies, connecting them in a delicate cosmic dance. The study of galactic collisions has been revolutionized by advancements in observational technology. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope have provided unprecedented views of colliding galaxies, revealing their intricate structures and the processes at play. Ground-based observatories equipped with adaptive optics and radio telescopes have also contributed significantly, enabling astronomers to study these events across a wide range of wavelengths. These observations, combined with theoretical models and simulations, have deepened our understanding of the physics of galactic interactions. One of the most intriguing aspects of galactic collisions is their potential to create new environments for the emergence of life. The redistribution of gas and the formation of new stars can lead to the creation of planetary systems in regions where conditions are conducive to life. While the direct effects of a collision on existing planetary systems are uncertain, it is conceivable that the gravitational perturbations and influx of material could spur the development of habitable environments. This possibility adds a profound dimension to our study of galactic collisions, linking them to the broader question of our cosmic origins. In addition to their scientific significance, galactic collisions have captured the imagination of artists, writers, and the public. These events, with their dramatic visual impact and immense scale, serve as a reminder of the grandeur and dynamism of the universe. They challenge our perception of time and space, inviting us to contemplate the vastness of the cosmos and our place within it. The study of galactic collisions is not only a pursuit of knowledge but also an exploration of the beauty and complexity of the natural world. The Milky Way's eventual collision with the Andromeda Galaxy offers a unique opportunity to observe such an event up close. Although this collision is billions of years away, its effects are already being studied through detailed simulations and comparisons with observed systems. These studies suggest that the resulting galaxy will likely be a large elliptical galaxy, potentially surrounded by a system of satellite galaxies. The fate of the solar system in this scenario is uncertain, but it is unlikely to be directly affected, as the vast distances between stars make direct collisions exceedingly rare. Beyond individual collisions, the study of galactic interactions provides insights into the large-scale structure of the universe. The distribution of galaxies in clusters and superclusters is shaped by their interactions, including mergers and accretions. Observing these structures allows astronomers to test theories of cosmology and the role of dark matter and dark energy in shaping the universe. Galactic collisions are thus not only events of local significance but also key to understanding the evolution of the cosmos as a whole. Galactic collisions also serve as cosmic laboratories for testing the laws of physics on massive scales. These interactions provide insights into fundamental forces, including gravity and hydrodynamics, under extreme conditions. For instance, by observing the behavior of gas, stars, and dark matter during a collision, astronomers can infer the properties of these components and test predictions from theoretical models. One particularly fascinating application is the study of dark matter. When galaxies collide, their stars and gas interact differently from their dark matter halos. By analyzing the spatial separation of these components, astronomers can infer the nature of dark matter and its role in shaping the universe. The bullet cluster is a prime example of how galactic collisions reveal the properties of dark matter. This system consists of two colliding galaxy clusters, with the hot gas from each cluster visible in X-rays. Observations show that the dark matter halos, traced by gravitational lensing, have passed through each other with minimal interaction, while the gas clouds have collided and slowed down. This separation provides strong evidence for the existence of dark matter and constrains its interaction cross-section. Studies like this underscore the importance of galactic collisions in advancing our understanding of the universe's most elusive components. As technology advances, simulations of galactic collisions have become increasingly sophisticated, providing detailed insights into their dynamics and outcomes. These simulations use complex algorithms to model the gravitational interactions of stars, gas, and dark matter, as well as the hydrodynamic behavior of gas clouds. By varying parameters such as galaxy mass, velocity, and angle of approach, researchers can explore a wide range of scenarios and compare the results to observations. Simulations have been instrumental in reproducing features such as tidal tails, starburst activity, and the formation of elliptical galaxies, validating our theoretical understanding of these processes. One of the most ambitious simulation projects is the Illustris TNG simulation, which models the evolution of the universe from shortly after the Big Bang to the present day. This project includes detailed treatments of galaxy formation, mergers, and feedback processes, providing a comprehensive view of the role of galactic collisions in cosmic evolution. By analyzing the data from such simulations, researchers can study the frequency and outcomes of galactic interactions across different epochs of the universe, shedding light on how these events have shaped the distribution and properties of galaxies. Galactic collisions are not limited to massive spiral and elliptical galaxies, they also occur among dwarf galaxies, the smaller counterparts that populate the universe in large numbers. Dwarf galaxy collisions are particularly intriguing because their lower masses make them more susceptible to external forces, leading to dramatic transformations. These interactions often result in the stripping of gas and stars, leaving behind irregular or disrupted structures. Studying dwarf galaxy collisions provides valuable insights into the role of interactions in shaping low-mass systems and their contribution to the overall galaxy population. One notable example of a dwarf galaxy collision is the Magellanic Stream, a massive trail of gas that extends from the Large and Small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way. This structure is thought to have formed as a result of interactions between the two galaxies and the Milky Way's gravitational influence. The Magellanic Stream serves as a natural laboratory for studying the dynamics of dwarf galaxy interactions and the processes that fuel the growth of larger galaxies like the Milky Way. As we look deeper into the cosmos, we also observe the remnants of ancient galactic collisions that occurred billions of years ago. These fossil records of interactions are preserved in the structures of galaxies, such as shells, ripples, and streams of stars. By studying these features, astronomers can reconstruct the history of past collisions and gain insights into the assembly of galaxies over cosmic time. The Milky Way itself bears evidence of such events, including streams of stars that trace the remnants of dwarf galaxies that were absorbed into its halo. These streams not only provide clues about the Milky Way's past but also offer a glimpse into the processes that govern galaxy assembly across the universe. Galactic collisions are also key to understanding the life cycle of galaxies. Over time, galaxies evolve through a series of mergers and interactions, transitioning from one type to another. For example, spiral galaxies like the Milky Way can merge to form elliptical galaxies, which are typically older and contain less gas for star formation. This process, known as hierarchical merging, is a fundamental aspect of cosmic evolution and helps explain the diversity of galaxy types observed in the universe today. By studying galactic collisions at different stages of evolution, astronomers can piece together the story of how galaxies grow, change, and ultimately fade away. On the largest scales, galactic collisions contribute to the formation of galaxy clusters and superclusters, the most massive structures in the universe. These structures are formed through the gradual accumulation of galaxies and dark matter, with collisions playing a central role in their growth. Observing these interactions provides insights into the dynamics of large-scale structure formation and the role of gravity in shaping the universe. For example, the Coma Cluster, a massive galaxy cluster located about 330 million light-years away, contains numerous examples of interacting and merging galaxies. Studying such systems helps astronomers understand the processes that govern the evolution of galaxy clusters and their role in the cosmic web. The future of galactic collision research is bright, with upcoming telescopes and observatories poised to revolutionize our understanding of these events. The Vera C. Rubin Observatory, set to begin operations in the coming years, will conduct a 10-year survey of the sky, capturing the motions and interactions of galaxies in unprecedented detail. The European Space Agency's Euclid mission will map the large-scale structure of the universe, providing new insights into the role of dark matter and dark energy in galactic collisions. These missions, along with advancements in computational power and simulation techniques, will enable astronomers to explore galactic collisions with greater precision and depth than ever before. The study of galactic collisions has not only deepened our understanding of the cosmos but has also reshaped our view of galaxies as dynamic, ever-evolving systems. In earlier eras of astronomy, galaxies were thought to be relatively static entities, existing in isolation. Observations of colliding systems, tidal features, and starbursts have revolutionized this perspective, revealing that interactions are a key driver of galactic evolution. Today, we know that galaxies are intricately connected, influencing each other through gravity, gas exchange, and the transfer of angular momentum. The interplay of gravity during a collision is a fundamental mechanism that dictates the trajectory and ultimate fate of the galaxies involved. When two galaxies approach each other, their mutual gravitational forces create complex tidal fields. These fields distort the galaxies, pulling stars, gas, and dust into new configurations. The tidal forces can also lead to the creation of unique structures, such as bridges of stars connecting the galaxies and vast streams of material trailing behind them. These tidal phenomena serve as visual signatures of galactic interactions and are often used to reconstruct the dynamics of past collisions. Another key feature of galactic collisions is the transformation of gas. Gas is the raw material for star formation, and its behavior during a collision has a profound impact on the resulting galaxy. In many cases, the gravitational forces compress gas clouds, triggering bursts of star formation that can outshine entire galaxies. However, collisions can also strip gas from galaxies, leaving them depleted and unable to form new stars. This gas stripping is particularly common in dense environments, such as galaxy clusters, where the combined gravitational pull of many galaxies can remove material from individual systems. A fascinating example of gas stripping is observed in the Virgo cluster, a nearby galaxy cluster containing thousands of galaxies. Some of these galaxies exhibit long tails of gas being removed by interactions with the cluster's hot intracluster medium, a process known as ram pressure stripping. These stripped galaxies often appear as red and dead systems, devoid of star-forming material and populated primarily by older stars. By studying such phenomena, astronomers gain insights into the environmental effects that shape galaxies in clusters and the broader role of interactions in galactic evolution. Galactic collisions are also closely tied to the growth and activity of supermassive black holes. As galaxies merge, their central black holes are drawn together by dynamical friction, eventually forming a binary system. During this process, the inflow of gas and dust toward the black holes can create spectacularly luminous active galactic nuclei, AGN. These AGN are among the brightest objects in the universe, powered by the release of gravitational energy as matter is accreted onto the black hole. The intense radiation from AGN can influence their host galaxies, driving powerful outflows of gas and suppressing further star formation, a feedback mechanism that plays a critical role in galaxy evolution. The final stages of a galactic collision often involve the complete merging of the two galaxies into a single system. This process can take billions of years, as the galaxies gradually lose energy and settle into a new equilibrium. The resulting galaxy often bears little resemblance to its progenitors, with features such as spiral arms or disks replaced by a smooth, elliptical structure. The merger also redistributes stars, gas, and dark matter, creating a more massive and dynamically complex system. Observing these final stages in other galaxies allows astronomers to predict the ultimate fate of our own Milky Way when it collides with the Andromeda Galaxy. The Milky Way-Andromeda collision, while still billions of years away, has been the subject of intense study. Simulations suggest that the collision will create a new galaxy, sometimes referred to as Milkomeda. The combined galaxy will likely be an elliptical system, surrounded by a halo of stars and dark matter. The solar system is expected to survive this event, though it may be relocated to a new orbit within the merged galaxy. Over time, the gas within the two galaxies will settle into the center, fueling new star formation before eventually being consumed. The resulting galaxy will likely evolve into a quiescent system, dominated by older stars. Beyond individual collisions, the study of galactic interactions contributes to our understanding of the large-scale structure of the universe. Galaxies are not randomly distributed but are organized into a cosmic web of filaments, clusters, and voids. Collisions and mergers play a critical role in shaping this structure, driving the growth of massive galaxy clusters and the formation of superclusters. Observing these processes provides valuable insights into the role of gravity and dark matter in shaping the universe on the largest scales. The cosmic web itself is a product of billions of years of galactic interactions. Filaments of dark matter, stretching across vast distances, act as highways for the movement of galaxies, funneling them into dense regions where collisions and mergers are more likely. These interactions fuel the growth of clusters, where galaxies continue to interact and evolve. The study of the cosmic web and its connection to galactic collisions is a vibrant area of research, with new discoveries constantly pushing the boundaries of our knowledge. The future of galactic collision research holds immense promise. Next-generation observatories, such as the Square Kilometre Array, SKA, and the Nancy Grace Roman Space Telescope, will provide unprecedented capabilities for studying these events. The SKA, a powerful radio telescope array, will enable detailed observations of gas dynamics during collisions, revealing the processes that drive star formation and feedback. The Roman Space Telescope, with its wide-field imaging capabilities, will survey vast regions of the sky, capturing the signatures of galactic interactions across cosmic time. In addition to observational advancements, improvements in simulation techniques will allow researchers to model galactic collisions with greater accuracy and complexity. These simulations will incorporate a wider range of physical processes, such as magnetic fields, cosmic rays, and detailed feedback mechanisms, providing a more comprehensive view of these events. By comparing simulations with observations, astronomers will refine their understanding of the fundamental processes that govern galactic evolution. Galactic collisions are among the most complex and transformative processes in the universe, encapsulating a wide array of physical phenomena. These events, spanning billions of years, have profound implications for the structure and evolution of galaxies, the distribution of matter, and the formation of stars. To expand on earlier discussions, let's delve deeper into the intricacies of galactic interactions, exploring the forces at play, their impact on the cosmic environment, and how they shape the observable universe. Gravity is the central force orchestrating galactic collisions. As two galaxies approach one another, their gravitational fields interact, creating tidal forces that distort their shapes and redistribute their contents. These tidal forces are responsible for some of the most visually striking features of galactic collisions, such as tidal tails, bridges, and shells. Tidal tails and stellar streams. Tidal tails are elongated structures formed when stars, gas, and dust are pulled out from the interacting galaxies. These tails can extend for hundreds of thousands of light-years and often serve as a record of the collision's dynamics. Stellar streams, similar to tidal tails, are composed primarily of stars and are typically observed as remnants of smaller galaxies that were torn apart and absorbed by larger ones. The Milky Way, for instance, contains numerous stellar streams, including the Sagittarius stream, which provides evidence of past collisions with dwarf galaxies. In elliptical galaxies, the remnants of galactic collisions can manifest as concentric shells or ripples. These features form when the stars of the merging galaxies settle into new orbits, creating wave-like patterns in the density of the stellar population. Observing these structures allows astronomers to reconstruct the history of the merger and understand the mechanisms that drive galaxy evolution. Gas is one of the most important components of a galaxy during a collision. Unlike stars, which are relatively unaffected by direct impacts due to their vast separation, gas clouds are much more likely to collide and interact. When galaxies collide, their gas clouds compress, triggering intense bursts of star formation. These starburst regions can produce millions of new stars within a relatively short time frame, dramatically altering the appearance and properties of the galaxies. The role of feedback mechanisms. While starbursts are a hallmark of galactic collisions, they are not the whole story. Massive stars formed during these bursts live short lives, ending in supernovae that release vast amounts of energy into the surrounding medium. This energy drives powerful winds, expelling gas from the galaxy and regulating future star formation. Additionally, active galactic nuclei, AGN, powered by the accretion of gas onto supermassive black holes, can emit jets and outflows that further influence the galactic environment. These feedback processes play a crucial role in shaping the evolution of galaxies, preventing them from forming too many stars too quickly and maintaining the balance of gas within the system. Ram pressure stripping. In dense environments in galaxy clusters, collisions are often accompanied by ram pressure stripping, a process where the hot, diffuse gas of the intracluster medium removes gas from individual galaxies. This stripping can quench star formation, leaving galaxies as red and dead systems dominated by older stars. The interplay between ram pressure stripping and tidal interactions in clusters adds another layer of complexity to the study of galactic collisions. Dark matter, an unseen but dominant component of galaxies, plays a pivotal role in galactic collisions. While stars and gas respond directly to collisions, dark matter interacts only through gravity, creating a unique dynamic. Observations of colliding galaxy clusters, such as the Bullet Cluster, have provided critical evidence for the existence of dark matter. In these systems, the stars and dark matter continue moving after the collision, while the gas, which collides and slows down, lags behind. The separation of these components allows astronomers to map the distribution of dark matter and study its properties. The role of dark matter halos. Dark matter halos, which envelop galaxies, act as gravitational anchors that influence the dynamics of collisions. These halos not only determine the trajectories of the colliding galaxies but also affect the formation of tidal features and the eventual merging process. Simulations of galactic collisions, which incorporate dark matter, have been instrumental in understanding how these halos shape the outcomes of interactions. Galaxies are not isolated entities but are embedded within the cosmic web, a vast network of filaments, clusters, and voids. This web, composed primarily of dark matter, dictates the distribution and motion of galaxies on large scales. Galactic collisions are particularly frequent in regions where filaments converge, funneling galaxies into dense clusters. These collisions contribute to the growth of galaxy clusters and the formation of superclusters, the largest structures in the universe. The role of filaments in galactic evolution. Filaments of the cosmic web act as highways for galaxies, guiding their motion and facilitating interactions. Observations of galaxies along these filaments have revealed that collisions and mergers are more common in these regions, highlighting their importance in driving the evolution of the cosmic landscape. Studying these interactions provides insights into the processes that shape the universe's large-scale structure. Galactic collisions are not evenly distributed throughout cosmic history. In the early universe, when galaxies were smaller and more abundant, collisions were more frequent. These interactions played a crucial role in the rapid growth of galaxies, fueling intense star formation and the assembly of larger systems. As the universe aged and galaxies grew larger, collisions became less common but more impactful, often resulting in the formation of massive elliptical galaxies. Fossil records of ancient collisions. The remnants of ancient galactic collisions are preserved in the structures of modern galaxies. By studying features such as tidal streams, shells, and stellar populations, astronomers can reconstruct the history of these events and gain insights into the processes that shape the universe. The Milky Way itself is a living fossil of past interactions, with its halo containing the remnants of dwarf galaxies that were absorbed over billions of years. Galactic collisions are dynamic and transformative events that drive the evolution of the universe on both small and large scales. When galaxies interact, the gravitational forces between them set off a cascade of changes that can last for billions of years. These processes, though slow from a human perspective, fundamentally reshape the galaxies involved, redistributing their stars, gas, and dark matter into new configurations. As the galaxies approach one another, their mutual gravitational attraction begins to distort their structures. These distortions are most evident in the formation of features like tidal tails, streams of stars and gas pulled outward by the interaction, and bridges of material connecting the galaxies. These phenomena not only provide striking visual evidence of the ongoing collision but also offer valuable clues about the masses, velocities, and trajectories of the interacting galaxies. The redistribution of gas is one of the most significant aspects of galactic collisions. Gas clouds within the colliding galaxies are compressed as they interact, often triggering bursts of star formation. These starburst events can produce thousands or even millions of new stars in a relatively short period, transforming the appearance of the galaxies. Regions of intense star formation often glow brightly in the ultraviolet and infrared wavelengths, revealing the activity hidden within the gas and dust. Observing these starburst regions provides astronomers with critical information about the physical processes that govern star formation and the life cycle of galaxies. While star formation is a key outcome of many galactic collisions, not all interactions are equally productive. In some cases, the gravitational forces strip gas from the galaxies, leaving them depleted and unable to form new stars. This process, known as gas stripping, is particularly common in dense environments like galaxy clusters. Here, the combined effects of tidal interactions and the intracluster medium, a hot and diffuse gas that permeates the cluster, remove gas from galaxies as they move through the cluster. The loss of gas effectively quenches star formation, leaving behind galaxies that are dominated by older, redder stars. The role of dark matter in galactic collisions cannot be overstated. While dark matter is invisible, its gravitational influence shapes the dynamics of the collision and the ultimate fate of the galaxies involved. Observations of colliding galaxy clusters, such as the Bullet Cluster, have revealed how dark matter behaves differently from ordinary matter during these events. While stars and dark matter pass through the collision relatively unimpeded, the hot gas in the galaxies collides and slows down, creating a separation between the components. This separation has provided some of the most compelling evidence for the existence of dark matter and has allowed astronomers to study its properties in unprecedented detail. As the collision progresses, the galaxies begin to merge, their structures becoming increasingly intertwined. Stars that were once part of distinct galaxies are now mixed together, forming new stellar populations that trace the history of the interaction. The merging process also draws the central supermassive black holes of the galaxies closer together. These black holes, surrounded by gas and dust, can ignite into active galactic nuclei, some of the most luminous objects in the universe. The intense radiation emitted during this phase can have profound effects on the surrounding gas, driving powerful outflows that regulate star formation and alter the evolution of the galaxy. Over time, the two galaxies settle into a new equilibrium, often forming a single, larger galaxy. The shape and structure of the resulting galaxy depend on the characteristics of the colliding galaxies and the nature of their interaction. Spiral galaxies, with their prominent disks and arms, often merge to form elliptical galaxies, which are more spherical and lack the distinct structure of their progenitors. These elliptical galaxies are typically populated by older stars, as much of the gas needed for new star formation has been consumed or expelled during the collision. The remnants of galactic collisions are not limited to the galaxies themselves. The interactions often leave behind trails of stars, gas, and dark matter that extend far beyond the main bodies of the galaxies. These features, known as tidal debris, can persist for billions of years, providing a lasting record of the collision. Observing these remnants allows astronomers to reconstruct the history of the interaction and understand the processes that shaped the galaxies. Galactic collisions are not confined to the present era. In the early universe, collisions were even more frequent, as galaxies were smaller and more numerous. These early interactions played a critical role in the assembly of larger galaxies and the growth of structures like galaxy clusters. Observations of distant galaxies, seen as they were billions of years ago, reveal the chaotic and dynamic nature of this era. By studying these distant systems, astronomers can trace the history of galactic evolution and understand how the universe has changed over time. The eventual collision between the Milky Way and the Andromeda Galaxy offers a glimpse into the future of our own galaxy. Currently separated by about 2.5 million light-years, the two galaxies are on a collision course, moving toward each other at a speed of approximately 110 kilometers per second. Over the next several billion years, the galaxies will approach one another, their mutual gravitational attraction distorting their structures and triggering bursts of star formation. Eventually, the two galaxies will merge, forming a new, larger galaxy that will likely resemble an elliptical galaxy. The solar system is expected to survive this event, but its position within the galaxy will change as the structure of the Milky Way is transformed. The study of galactic collisions has been revolutionized by advancements in observational technology. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope have provided detailed views of colliding galaxies, capturing their intricate structures and the processes at play. Ground-based observatories, equipped with adaptive optics and radio telescopes, have complemented these observations, revealing the dynamics of gas and dark matter during collisions. These observations, combined with computer simulations, have allowed astronomers to explore the complex interplay of forces that shape galaxies and the universe. Simulations of galactic collisions have become increasingly sophisticated, incorporating a wide range of physical processes, from the behavior of gas and stars to the influence of dark matter and supermassive black holes. These simulations allow researchers to test different scenarios and compare the results with observations, providing valuable insights into the mechanisms driving galactic evolution. By varying parameters such as galaxy mass, velocity, and orientation, astronomers can explore the diversity of outcomes and gain a deeper understanding of the factors that shape galaxies. Galactic collisions are more than just dramatic cosmic events, they are engines of transformation, drivers of evolution, and windows into the very mechanisms that govern the universe. They encapsulate the interconnected nature of the cosmos, where nothing is static, and everything is in flux. While each collision is unique, governed by the specific conditions of the interacting galaxies, They all follow the universal laws of physics, providing astronomers with a natural laboratory for studying gravitational dynamics, star formation, and the mysterious nature of dark matter and dark energy. In many cases, galactic collisions act as the beginning of a new chapter in the life of a galaxy. For example, a small satellite galaxy merging with a larger host, like the Milky Way, might introduce fresh gas, reigniting star formation. Such interactions can seed the host galaxy with clusters of young stars or even stimulate the growth of its central supermassive black hole. These smaller mergers, sometimes called minor mergers, are less disruptive than the collision of two similarly sized galaxies, known as major mergers, yet they can still leave a lasting imprint on the galaxy structure and stellar population. Evidence of these minor mergers is visible in our own galaxy. The Sagittarius dwarf spheroidal galaxy, currently being torn apart by the Milky Way's gravity, has left streams of stars that weave through our galaxy's halo. These stellar streams are not just remnants of past mergers, they are clues to the Milky Way's assembly history and its interaction with its smaller companions. By studying these streams, astronomers can reconstruct the Milky Way's growth over billions of years and better understand the role of mergers in building its present structure. Major mergers, on the other hand, often lead to the most dramatic transformations. When two massive galaxies collide, their disks are typically destroyed, and the resulting galaxy takes on a more spheroidal shape, becoming what astronomers classify as an elliptical galaxy. These major mergers are also responsible for the most spectacular tidal tails, bridges, and other features that light up the cosmos. In some cases, these features can be seen long after the galaxies have coalesced, offering a fossilized record of the event. Elliptical galaxies formed through such mergers are often rich in stars but poor in gas. This gas is either consumed during the starburst phase of the merger or expelled by the feedback effects of supernovae and active galactic nuclei. Without sufficient gas to form new stars, these galaxies enter a quiescent phase, where star formation ceases, and the galaxy slowly fades as its stars age. The color and brightness of these systems, dominated by older, redder stars, stand in stark contrast to the bright, blue, star-forming regions of their progenitors. However, not all collisions end with the merging of galaxies. Some galaxies, particularly those in high-velocity encounters, may pass through one another without coalescing. These flyby interactions can still have significant effects, stripping gas, triggering bursts of star formation, and reshaping the galaxy structures. Such encounters are common in dense environments like galaxy clusters, where the gravitational influence of nearby galaxies creates a dynamic and chaotic environment. Galaxy clusters themselves are sites of some of the most massive and energetic collisions in the universe. When clusters of galaxies collide, the interactions are on a scale far beyond individual galaxies. These events involve trillions of stars, enormous quantities of hot gas, and vast amounts of dark matter. Observations of colliding clusters, such as the Bullet cluster and the ongoing merger in the Abell 520 system, have provided critical insights into the nature of dark matter and the distribution of mass in the universe. In these cluster-scale collisions, the stars of individual galaxies largely pass through each other unscathed, but the hot gas that fills the intracluster medium interacts violently. This gas slows down and heats up, emitting X-rays that can be observed with space-based telescopes like Chandra and XM Newton. The separation between the gas and the dark matter halos, which continue moving largely unaffected, creates a unique observational signature that has helped confirm the existence of dark matter. The role of galactic collisions in shaping the universe extends to the cosmic web itself. The large-scale structure of the universe, with its filaments, clusters, and voids, is the result of billions of years of gravitational interactions. As galaxies are funneled along filaments into dense clusters, collisions and mergers become more frequent, driving the growth of these massive structures. Observing the cosmic web provides a broader context for understanding galactic collisions, linking these local events to the global evolution of the universe. In addition to their scientific importance, galactic collisions are a source of wonder and inspiration. Their immense scale, spanning hundreds of thousands of light-years, and their slow-motion choreography over billions of years, challenge human imagination and redefine our perception of time and space. Artists and writers have drawn upon the imagery and dynamics of these collisions, finding in them metaphors for transformation, destruction, and renewal. The public fascination with these events is a testament to their ability to connect us with the grandeur of the cosmos. As we look to the future, the study of galactic collisions is poised for significant advancements. Next-generation telescopes, such as the Extremely Large Telescope (ELT) and the Square Kilometre Array (SKA), will provide unprecedented resolution and sensitivity, enabling detailed studies of these events across the electromagnetic spectrum. These observations, combined with increasingly sophisticated simulations, will allow astronomers to probe the finer details of galactic interactions, from the behavior of individual gas clouds to the role of dark matter halos. Moreover, the discovery of gravitational waves has opened a new window on the universe, offering the potential to study the mergers of compact objects, such as black holes and neutron stars, that may occur during galactic collisions. These observations could provide insights into the final stages of galaxy mergers and the environments in which these compact objects form and evolve. As we continue to explore the universe, galactic collisions remind us of the dynamic and interconnected nature of the cosmos. They are a testament to the power of gravity, the complexity of matter, and the beauty of cosmic evolution. By studying these events, we not only uncover the mechanisms that shape galaxies but also deepen our understanding of the universe as a whole, connecting us to its vast and ever-changing story. Galactic collisions provide some of the most profound insights into the underlying physics that governs the evolution of large-scale structures in the universe. These events serve as natural experiments where astronomers can study the behavior of galaxies, gas, dark matter, and stars under extreme conditions. They offer a unique opportunity to probe the fundamental forces that shape the cosmos, and with each collision, astronomers are uncovering more details that help us understand both the past and the future of our universe. One of the most intriguing aspects of galactic collisions is the behavior of dark matter during these interactions. Dark matter, which accounts for about 85% of the total matter in the universe, does not interact electromagnetically, meaning it does not emit, absorb, or reflect light. As a result, it remains invisible to telescopes. However, its gravitational influence on visible matter is undeniable, and its effects during galactic collisions are a critical part of understanding how galaxies and galaxy clusters evolve. During a collision, the dark matter halos of the interacting galaxies are not significantly affected by the collision. Unlike stars and gas, which are influenced by tidal forces and gravity, dark matter interacts only gravitationally. This results in the dark matter halos passing through one another largely unaffected, while the gas and stars may collide and merge. The bullet cluster, an example of two galaxy clusters colliding, provide strong evidence for dark matter's existence and behavior. In this system, the dark matter has been mapped through gravitational lensing, which shows a separation between the dark matter and the colliding gas, further confirming that dark matter does not interact in the same way as normal matter. These types of observations are crucial for understanding the nature of dark matter. While its presence is inferred from its gravitational effects, its exact composition remains one of the greatest mysteries in astrophysics. The behavior of dark matter during galactic collisions offers an important clue. Its inability to interact via electromagnetic forces suggests that it is likely made up of particles that do not emit or absorb light, which is in line with theories of weakly interacting massive particles, WIMPs, or axions, among other candidates. Another crucial feature of galactic collisions is the formation of supermassive black holes at the centers of galaxies. Supermassive black holes, which can have masses ranging from millions to billions of times the mass of our Sun, are found in the centers of most galaxies, including the Milky Way. These black holes are thought to have formed in the early stages of galaxy formation, with their growth potentially driven by galaxy mergers. As galaxies collide and their central black holes draw closer together, they eventually merge into a single, more massive black hole. During this process, a significant amount of energy is released in the form of gravitational waves, ripples in spacetime caused by the acceleration of massive objects. The merger of black holes has already been detected by gravitational wave observatories like LIGO and Virgo, and such events are expected to become even more detectable as the sensitivity of these instruments improves. The collision of two supermassive black holes is also likely to release enormous amounts of energy in the form of light and other radiation, including the emission of jets from the newly formed black hole. The study of supermassive black holes and their role in galactic mergers is important for understanding how galaxies evolve and how their central regions are shaped. These black holes are often the driving force behind the active galactic nuclei, AGN, extremely energetic regions surrounding black holes, where matter is being accreted. The process of accretion, matter being drawn into the black hole, releases vast amounts of energy, which can influence the surrounding galaxy. AGN activity can trigger star formation in some cases but can also quench star formation by expelling gas and dust from the galaxy. This feedback mechanism plays a key role in regulating the growth of galaxies and their central black holes. Galactic collisions are some of the most efficient processes for triggering star formation. As galaxies collide, the gas clouds within them are compressed due to the tidal forces of the collision. This compression leads to the collapse of molecular clouds and, in turn, to the formation of new stars. The gas in these clouds is typically cold and dense, and under the right conditions, the gas can collapse to form clusters of young, hot stars. These starburst regions are often observed as bright, blue regions in the galaxy, and they represent an explosive phase of star formation. However, the feedback from these starburst regions is not a one-way process. As massive stars are formed, they eventually burn through their fuel and explode as supernovae, releasing vast amounts of energy into the surrounding gas. This energy can drive powerful winds that expel gas from the galaxy, essentially shutting down the star formation process. The feedback from supernovae and the central active galactic nuclei, AGN, can regulate the growth of the galaxy and control the amount of gas available for star formation. This process is known as star formation feedback and is a fundamental aspect of how galaxies evolve over time. The balance between star formation and the expulsion of gas is one of the key factors in determining the type of galaxy that forms after a collision. If a galaxy retains enough gas, star formation can continue for billions of years, leading to the growth of a large spiral galaxy. However, if the gas is expelled too quickly, the galaxy can become quenched, ceasing star formation and becoming an elliptical galaxy, composed mostly of older stars. These transitions can be observed in real time in colliding galaxies, and studying these transformations provides insight into the broader mechanisms of galactic evolution. The eventual outcome of a galactic collision depends on the properties of the interacting galaxies. The interaction of two spiral galaxies, such as the impending collision between the Milky Way and the Andromeda Galaxy, will likely result in the creation of an elliptical galaxy. The initial spiral structure of both galaxies will be destroyed, and the merger will lead to a more rounded, spheroidal shape. The gas within the galaxies will be compressed and consumed, leading to bursts of star formation before the gas is largely depleted. The central supermassive black holes will merge, forming an even more massive black hole at the center of the new galaxy. Elliptical galaxies formed through such mergers are often red and dead, with very little new star formation occurring. These galaxies are dominated by older stars, and their lack of gas means they cannot produce new stars at the same rate as spiral galaxies. Over time, these galaxies become more and more quiescent, with only a small number of stars continuing to form in the remaining pockets of gas. As a result, elliptical galaxies are often the final stage in the life cycle of many galaxies, marking the end of a long history of star formation. In contrast, minor mergers, where a smaller galaxy merges with a much larger one, often result in less dramatic transformations. These mergers tend to trigger bursts of star formation but do not significantly alter the large-scale structure of the larger galaxy. The smaller galaxy's gas is often consumed during the process, adding to the stellar population of the larger galaxy. This process can also introduce new stars, such as globular clusters, into the host galaxy's halo, creating a more complex stellar system. The future of galactic collisions will continue to shape the universe in profound ways. As the universe ages and galaxies continue to interact and merge, the landscape of the cosmos will continue to evolve. These events remind us that, on cosmic timescales, galaxies are not static entities but dynamic systems in a constant state of change. From the formation of new stars to the growth of supermassive black holes, galactic collisions play a central role in shaping the universe as we know it. Galactic collisions continue to serve as an invaluable lens through which astronomers study the life cycles of galaxies and the broader processes that govern cosmic evolution. These interactions not only transform individual galaxies but also contribute to the larger-scale dynamics of the universe. As we delve deeper into these monumental events, several key areas of research emerge that are driving our understanding of the cosmos forward. The role of mergers in galaxy clusters is one of the most critical areas of study. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies, as well as massive amounts of dark matter and hot gas. Within these clusters, galactic collisions are frequent, driven by the dense environment where galaxies are in close proximity. The resulting interactions shape not just the individual galaxies but the overall structure and evolution of the cluster itself. One significant phenomenon in clusters is cannibalism, where a massive central galaxy, often called a brightest cluster galaxy, BCG, grows by consuming smaller satellite galaxies. This process leads to the central galaxy becoming disproportionately large compared to its neighbors. These BCGs often contain vast amounts of stellar mass and host some of the most massive supermassive black holes in the universe. The collisions that fuel their growth are often accompanied by the stripping of gas and stars from smaller galaxies, enriching the intracluster medium with heavy elements. The intracluster medium, ICM, itself plays a central role in the dynamics of galaxy clusters. This hot, X-ray emitting gas pervades the space between galaxies in clusters and serves as a record of their interaction history. During collisions, the gas from the merging galaxies is often stripped away, mixing with the ICM and triggering shock waves that propagate through the cluster. These shock waves, which can extend for millions of light-years, heat the gas to extreme temperatures and alter its distribution. Observing these shock fronts provides astronomers with a unique opportunity to study the physics of high-energy processes on a massive scale. One of the most striking examples of shock waves in galaxy clusters is found in the Bullet cluster. This system, created by the collision of two galaxy clusters, features a prominent bow-shaped shock wave in the intracluster gas. Observations of the Bullet cluster have not only shed light on the dynamics of cluster collisions but also provided some of the strongest evidence for the existence of dark matter. By mapping the separation between the dark matter, stars, and gas, astronomers have demonstrated that dark matter behaves differently from ordinary matter during these interactions. Beyond clusters, galactic collisions are also essential for understanding the chemical evolution of the universe. The redistribution of gas during collisions leads to the mixing of chemical elements, enriching galaxies with the heavier elements produced in stars. This process, known as metal enrichment, plays a critical role in the formation of planets and the potential for life. Metals like carbon, oxygen, and iron are formed in the cores of stars and are dispersed into the surrounding medium during supernova explosions. Galactic collisions accelerate this enrichment process by triggering star formation and distributing the resulting metals throughout the galaxy. In addition to star formation, the growth of supermassive black holes during galactic mergers also contributes to the chemical evolution of galaxies. As gas falls into the black hole's accretion disk, some of it is funneled outward in the form of powerful jets and outflows. These jets can travel vast distances, carrying metals and energy into the galaxy's halo and beyond. The interplay between black hole activity and the surrounding environment is a key area of research, as it has far-reaching implications for the regulation of star formation and the evolution of galaxies. Observations across the electromagnetic spectrum have been instrumental in uncovering the details of galactic collisions. Each wavelength reveals a different aspect of these interactions. In the optical range, astronomers observe the distribution of stars and the tidal features that result from gravitational interactions. Infrared observations, such as those conducted by the Spitzer Space Telescope and the James Webb Space Telescope, reveal the heat emitted by dust clouds warmed by newly formed stars. X-ray telescopes like Chandra and XMM Newton provide insights into the hot gas in the intracluster medium and the energetic processes associated with supernovae and active galactic nuclei. Meanwhile, radio telescopes like ALMA probe the cold molecular gas that serves as the raw material for star formation. Simulations have also emerged as a cornerstone of modern astrophysics, allowing researchers to model the complex dynamics of galactic collisions. These simulations incorporate a wide range of physical processes, including gravity, hydrodynamics, star formation, and feedback mechanisms. By running simulations with varying parameters, astronomers can explore how factors such as galaxy mass, gas content, and collision angle influenced the outcome of a merger. High-resolution simulations have successfully reproduced many observed features of galactic collisions, such as tidal tails, starbursts, and the formation of elliptical galaxies, providing strong validation for our theoretical models. One of the most ambitious projects in this field is the illustrious TNG simulation, which tracks the evolution of thousands of galaxies over billions of years. This simulation includes detailed models of star formation, black hole activity, and dark matter interactions, offering a comprehensive view of how galaxies grow and change over time. By comparing the results of such simulations with observations, astronomers can refine their understanding of the physical processes that govern galactic collisions and their broader role in the cosmos. The impending collision between the Milky Way and the Andromeda Galaxy serves as a natural laboratory for studying the long-term effects of a major merger. Current models predict that the collision will begin in about 4.5 billion years, culminating in the formation of a single, larger galaxy over the course of several billion years. Simulations suggest that the resulting galaxy, often referred to as Milkomeda, will be an elliptical galaxy with a smooth, spheroidal structure. The gas within the galaxies will be largely consumed or expelled during the collision, leading to a decline in star formation over time. While the prospect of such a collision might seem catastrophic, it is important to remember that the vast distances between stars make direct stellar collisions extremely rare. Instead, the gravitational interactions will reshape the structure of the galaxies, mixing their stellar populations and redistributing their gas and dark matter. The Sun, along with the rest of the solar system, is expected to survive the collision, although its position within the new galaxy may change. The night sky from Earth, or whatever habitable planets may exist in the distant future, will be transformed, filled with the light of countless new stars and the remnants of the collision. Looking further into the future, galactic collisions will continue to shape the universe for billions of years to come. As the expansion of the universe accelerates due to dark energy, interactions between galaxies within clusters and groups will become increasingly isolated. Eventually, the remaining galaxies in clusters like the Virgo cluster, to which the Milky Way belongs, may coalesce into a single massive galaxy, marking the final stage of their evolution. Through the study of galactic collisions, astronomers are not only uncovering the processes that drive the evolution of galaxies but also gaining deeper insights into the fundamental nature of the universe. These events, which span billions of years and involve unimaginable scales of energy and matter, are a testament to the power of gravity, the creativity of nature, and the interconnectedness of the cosmos. As we continue to explore these cosmic collisions, we deepen our understanding of the universe's history, its present state, and its ultimate fate. The study of galactic collisions brings into focus the profound dynamism of the cosmos. These events, unfolding over billions of years, are not just spectacles of destruction but engines of creation and transformation. By examining the interactions between galaxies, we uncover the mechanisms that drive the evolution of stars, the redistribution of matter, and the growth of cosmic structures. Yet, galactic collisions also serve as a microcosm for the interconnectedness of the universe, revealing how local interactions ripple out to shape the broader fabric of space and time. As we refine our understanding of galactic collisions, the questions they raise challenge us to think on scales far beyond human experience. How do these colossal events shape the future of the universe? What role do they play in seeding the conditions for life? And how can the lessons we learn from them deepen our understanding of the fundamental forces that govern everything from the smallest particles to the largest cosmic structures? Galactic collisions are intrinsically linked to the long-term fate of the universe. As the cosmos expands, driven by the mysterious force of dark energy, galaxies that are gravitationally bound to each other will continue to collide and merge. However, on the largest scales, the accelerated expansion of the universe will increasingly isolate galaxy groups and clusters. Over trillions of years, as star formation dwindles and galaxies grow dim, the universe will transition into a quieter, more quiescent state. Yet, even in this far-future cosmos, the echoes of ancient galactic collisions will remain imprinted in the distribution of stars, gas, and dark matter. These distant horizons remind us that galactic collisions are not isolated phenomena but part of a continuum that connects the past, present, and future of the universe. In the early universe, collisions played a pivotal role in the formation of the first large galaxies, forging the structures that would eventually become the cosmic web. In the present era, collisions drive the evolution of galaxies, sparking bursts of star formation, igniting active galactic nuclei, and redistributing matter on vast scales. And in the distant future, the remnants of these collisions will persist as silent witnesses to a universe that has grown old. The study of galactic collisions also forces us to confront the fundamental questions of our own existence. The chemical elements that make up life on Earth, carbon, oxygen, iron, and more, were forged in the hearts of stars, scattered into space by supernova explosions, and redistributed through processes like galactic collisions. These events have not only shaped the galaxies but also set the stage for the formation of planets and the emergence of life. In this sense, the story of galactic collisions is also the story of our cosmic origins. Observing galactic collisions also challenges our perception of time. On human timescales, these events are almost imperceptibly slow, unfolding over millions or billions of years. Yet, through the power of telescopes and simulations, we can compress these vast epochs into moments, witnessing the birth of new stars, the growth of black holes, and the reshaping of galaxies. This ability to observe and understand phenomena that transcend human timescales underscores the unique role of science in bridging the gap between the microscopic and the cosmic, the fleeting and the eternal. The future of galactic collision research is as vast as the universe itself. With next-generation observatories like the James Webb Space Telescope, the Vera C. Rubin Observatory, and a square-kilometer array, humanity stands on the brink of an era of unprecedented discovery. These instruments will allow us to observe collisions in greater detail, map the distribution of dark matter more precisely, and probe the environments of galaxies at earlier and later stages in their evolution. Combined with advancements in computational modeling, these observations will refine our understanding of the physics of galactic interactions and deepen our appreciation for the complexity of the cosmos. Ultimately, galactic collisions remind us of the universe's dual nature, a place of immense violence and profound beauty, where destruction and creation are inextricably linked. They challenge us to think beyond the immediate and the familiar, to embrace the vastness of space and time, and to marvel at the forces that have shaped and will continue to shape the cosmos. By studying these colossal interactions, we come closer to answering some of the most fundamental questions about the universe. How did it come to be? How does it work? And what is our place within it? In the end, galactic collisions are more than just astronomical phenomena. They are cosmic narratives that span the ages, weaving together the threads of gravity, matter, and energy into the tapestry of the universe. As we look to the stars and galaxies around us, we are reminded that we, too, are part of this story, shaped by the same forces that sculpt the cosmos. Through the study of galactic collisions, we gain not only a deeper understanding of the universe but also a profound sense of connection to the grand, unfolding drama of existence itself.